Hi, and welcome to the virtual version of the Geometric Optics and the Eye Lab. Please make sure that you've watched the pre-lab lecture on video and also read the background section of the lab instructions before watching this video. As you go through this video, I'll essentially be walking you through the same exercises you would have been doing had you been here in person. But throughout, I will be adding little concept tests. To get the most educational value from this, it's really important that you actually pause the video after I pose each concept test. Think about it on your own for a while, and only when you think you've gotten the answer or are so confused that you don't think you're going to be able to, which is fine, then unpause the video and see what I say. I hope you enjoy it. In the conventional version of this lab, we would have you investigate Snell's law quantitatively with this apparatus, but in this version of the lab we're only going to look at it qualitatively. So over here we have a light source which is shining light through a slit, so that gives us this beam that we can see on this table that can rotate, and right in the middle of that table I have mounted this piece of plastic which is sort of half of a cylinder, so it's flat on one side and circular on the other. Okay, let me get you oriented in this top view. We've got the incident beam coming in here. Here's our half circle shaped piece of plastic, and here's the outgoing beam. Right now there's no refraction happening because the incident beam is normal to this surface and also normal to the back surface. Normal meaning perpendicular in this case. So let me rotate this. I'll maybe rotate it by about 45 degrees. So now you can see the incoming beam is being refracted. So they have marked this line on the disc, which is the normal. And so you could see if we projected the incoming beam, it would go this way, but it's being refracted toward the normal because it's moving from air into the plastic, which is the medium with the higher index of refraction. I think you can also see this reflected beam. If I keep on going, the amount of refraction gets bigger, and now, and you could of course calculate that the angle of the refraction using Snell's law. So now let's switch so that we're coming in on the curved side. And again, we'll start with it coming in at normal incidence, so there's no refraction. As I start to rotate, let's now see that the incident beam, if it were to continue, would go this way. And here's the normal, so you can see it's being refracted away from the normal as it exits the flat side, right? It's always perpendicular to the curved side, but as it exits the flat side, it's being refracted away from the normal, as is appropriate for going from a high index medium to a low index medium. Here's the reflection over here. If I keep on going, rotating to more and more grazing incidence, you can see that the refracted beam is almost parallel with the flat side of the piece of plastic. If I go a little bit further, right now it is essentially parallel, and now if I go even a little bit further, the refracted beam is now gone because the index of refraction, if you tried to use Snell's law to calculate that angle, there would be no real solution to it. And notice that the reflected beam is brighter now. Let me go backwards just a little bit, rotate backwards. So here, where I'm almost at that point where the refracted beam is parallel, some of the light is going here and some here, so the intensity is being split between these two. But as soon as I go just beyond that, this one becomes stronger. And so that's the phenomenon of total internal reflection. Okay, here's the apparatus we're going to be using for the next couple of experiments. We've got this light source, which, let's see if I can get this to show it to you. Yes, it's got this pattern of two concentric circles and one arrow that points up and one arrow that points to the right on it. And then we've got various lenses like this one that we can snap into the place on the rails. So these are relatively inexpensive lenses, but each one is marked. So this is a 100 millimeter focal length lens, and I can snap it into place in the rails, so it's very convenient. And you'll notice that it's got a little pointer on it which measures the position of the center of the lens. Similarly, the position of the light source can be read off of this meter stick that's built into the optical rail. So for instance, right now that's right at the 36 centimeter mark. And then finally we've got this, which I can snap into place, which is a screen which we can use to detect images. Okay, I've got the room lights dimmed so that we can see what's going on a little bit better. So remember, here is our light source with the two concentric circles and the arrows on it. And right now I've got no lens in place, I just have the screen. And I just want to show you that right now, no matter where I put the screen, I'm moving it closer and closer to the source. And you can see that it's getting lit up more and more, but we never see that pattern of the two concentric circles and the arrows on it. Okay, now for our first experiment, I'm going to take this 100 millimeter focal length lens that I showed you before, and I'm going to snap it in so that and I'm going to position it at the 50 centimeter mark, so 500 millimeters. So the 100 millimeter focal length lens is positioned right at the 50 centimeter mark. I'm going to position the light source with the two concentric circles and the arrows on it at the 35 centimeter mark. So that's right there at 35 centimeters. Now I want you to, I'm going to ask you a question, which is to predict where should there be an image formed of this two concentric circles and arrows pattern. At what centimeter marking should that image be formed? So pause the video now, think about this, talk it over with your partner if you have one, and only after you think you've got an answer, come back. Okay, let's find out experimentally. So I'm going to slowly move the screen towards the lens, and as I move it in, maybe you can see something is starting to happen. We're starting to see the image form, and it forms right about there. So before I even try to get a really quantitative measurement, I want you to notice that now things are upside down. So the arrow that used to point upwards has now been flipped so that it's pointing downwards. And also things have been flipped left to right. So the arrow still looks like it's pointing to the right, but remember, I'm now looking in the opposite direction. So if I try to step back on this side where the source is, can we see this? Yes. The arrow there is pointing away from us, whereas if I look at the screen, now the arrow is pointing towards us. So the pattern has been flipped left to right and up to down. Now let's try to figure out where exactly it comes to the best focus. So often when you're trying to do an experiment like this, the way you want to do it is find there, that's definitely out of focus. There, that's out of focus. If I find two places where it's roughly the same amount out of focus and then go halfway in between, that's often the most accurate way of finding the sort of sweet spot. So it's right about here. There's definitely some uncertainty. I would say maybe a half a centimeter uncertainty in my measurement. And let's see what we got. It's at about 80.3 centimeters. So if you've done the calculations, you can put down on the sheet how well that corresponds to what you calculated. Now let's also measure the magnification. So to measure the magnification, I'm going to first zoom in on the source, the light source, and then I'm just going to use some calipers to measure the diameter of the larger circle. Let me check the 0. That's pretty good. All right, so I get 20.00 millimeters. So now I want you to predict how big should that larger circle be when I make the measurement on the screen. So pause the video now, make that prediction, and then come back. Okay, so now I've changed the angle of the camera, so we're looking at the screen. I'll zoom in on the screen, and then I'm going to use my calipers to measure the diameter of that larger circle on the screen. I get 41.02 millimeters. Remember, I've got the screen positioned at 80.3 centimeters, which was experimentally, as far as I could tell, the best place of best focus. Okay, so for this next exercise, we are positioning the light source closer to the lens than its focal length. So this is the same 100 millimeter focal length lens, and this is the light source, and you can maybe see that I've got the lens positioned right on the 0 centimeter mark, and the light source is positioned on the 7 millimeter mark. So now I'm going to move the camera so that you can be looking right into the lens. Okay, I'm blocking the light with my hand so that the auto exposure on the camera will allow you to see the setup. We're looking straight into the lens, and then when I unblock it, the auto exposure will readjust, and there you can see the image as seen through the lens. You can see that the arrows are pointing in their original directions, up and to the right. Now I'm going to remove the lens. So I don't know, yeah, I guess you can barely see my hand. I'm going to remove the lens, and now you can see that it is considerably smaller than it used to be. Okay, now we're going to build a simple microscope. For our objective lens of the microscope, we're going to use this lens, which is labeled 50 millimeters, but it turns out it's not quite right, so we're going to measure its focal length experimentally. So I have positioned that lens so it's on the 30 centimeter mark. I've got our light source. Let's put it right on the 40 centimeter mark, and then I'm going to install our screen, and we'll come over here and turn off the lights and find where the image is formed. Okay, so now I've got the room lights off. I will zoom in on the screen. I think that's right. And then I'm going to move it, shift it back and forth until we find where the image is formed. And it's in the best focus. Right about there, which is at the 21.6 millimeter mark on the scale. So from that, figure out what the focal length of this lens is, and then come back. Okay, so I got 4.9 centimeters, so pretty close, but slightly off. So next question is, when we're going to build a microscope, should I put the object where we're trying to image it, let's say right there is 4.9 centimeters away, so that's right at the focal length. Is that where I want it? Do I want it a little bit further away than that, a lot further away than that, a little bit closer than the focal length, or a lot closer than the focal length? So pause the video, think about that, and then come back. So we want it to be a little bit further away than the focal length. So I'm going to put it 8 centimeters away. So at the 38 centimeter mark. In a real microscope, you would use a much shorter focal length lens. It might have a focal length of maybe several millimeters instead of 50 millimeters. But the percent distance further away is still about right. So now, if this is 8 centimeters away and we've got our 4.9 centimeter focal length lens, where do you predict the image is going to be formed. So along this numerical scale, given that the lens is 30, where should the image be formed? So make that prediction, pause the video, and then come back. Okay, so we're back here looking at the screen. I got in my calculations that the image would be formed 12.6 centimeters away from the lens. So that would put it at the 17.4 centimeter mark. In fact, it's formed a little bit, the best focus is a little bit further away than that, maybe at the 15.7 centimeter mark, something like that, but pretty close. So now let's think about where do we want to put our eyepiece. So I've got the screen positioned where the image is being formed. Should I put the eyepiece closer to the objective lens than the screen or farther away? Pause the video and then come back. I want it to be farther away. In fact, I want it to be, this eyepiece is supposed to act as a magnifying lens looking at that image that's being formed. So I want it a little bit closer than its focal length, which is nominally 50 millimeters. I want it about, let's say, 40 millimeters away from where that image is formed. Okay, so here we are looking into the eyepiece of our microscope. We are looking at the image of the magnified image of the millimeter ruling that appears on the light source. So you can see that it's been greatly magnified. The lenses that we're using are very inexpensive, and so things are not in focus over a very broad range, left and right and up and down. You can also see that there's a distortion, that different colors are focused in different ways. That effect is called chromatic aberration, meaning that the focal length of these lenses depends on the wavelength. That's true for all lenses, but you can buy more expensive lenses in which they have tried to compensate for that to the degree possible, which are called achromats, meaning not colored or not dependent on color. Okay, next we're going to build a simple telescope. We're going to be using this lens, which has a focal length of 250 millimeters, i.e. 25 centimeters. And we're going to try to look at the secret message written on this piece of paper. So as a concept test, I want you to think about where should we put the eyepiece. The objective lens I have positioned at the 30 centimeter mark. And remember, it has a focal length of 25 millimeters. We're going to be using an eyepiece that has a focal length of 5 centimeters. So where along here should I put that? Pause the video, think about it, and then come back. Okay, so this is a 25 centimeter lens. That means since our object is essentially infinitely far away, the image should be formed 25 centimeters away from the lens, which would be at the 5 centimeter mark. And so then I want to put my eyepiece a little bit closer than 5 centimeters away, since it's a 5 centimeter focal length eyepiece. Okay, so here we are looking through the eyepiece of our telescope, and you can see the secret message, which of course has been inverted because of the action of the telescope. All right, so next we're going to be doing experiments with this model of the human eye. You can see at the front there is the lens which simulates the cornea. We've got slots here in which we can put lenses to simulate the lenses of eyeglasses. In here there are 3 slots where we can put lenses to simulate what's called the crystalline lens of the eye. And then there are slots at the back where we can put this piece, which is there to simulate the retina. So I'm going to start by putting it in the slot that's labeled normal. So I hope you can read those indicators. Let me turn it around so they're right side up. So that means that there's now sort of the normal distance between the retina and the cornea. And then as directed, we're going to put, we've got these various different lenses I'm going to take the lens that is labeled 120 millimeter focal length and put that into the slot near the front of the model that's labeled septum, like so. And next we're going to fill the model with water. So since there's just me here, I'm going to take it over to the sink and fill it with water. This is to simulate the fluid that is inside your eyeball. So here we go. Fill it right up. There we go. I'm going to pour out a little bit more so I don't make too much of a mess. Okay. Let's take it back over here. Okay, here's what we're going to be using as the thing we're going to image in the eye. It's just the window, and to help keep things oriented, I put that little gooseneck lamp right in front of it. And so now here's the eye, which I have positioned looking at the window, and let's zoom in on the image and fix the focus. Okay, and there is the image being formed on the retina. For this part of the experiment, it will work better to have a brighter source, brighter object. So we're going to use this gooseneck lamp, and you can see that I have written the word top on the top part of the bulb in blue marker. So we're going to shine this at our eye model, like so. And I'm going to show you the view from up here. I'll turn off those overhead lights so that you don't get that distracting reflection, and we'll be able to zoom in nicely. And I'm going to set the camera for manual focus so that the only focus changes that you'll be seeing will be due to the things I do with the lenses in the eye. Okay, so we're set with the light source, the object, 35 centimeters from the cornea, and the camera is now focused on the retina, and you can see that it is indeed in pretty good focus. You can also see the word that I wrote top on the top of the bulb is now actually at the bottom. So now we're going to move, it says move the eye model as close as possible to the light source, but it's easier for me to move the light source in. So I'm going to move the light source in, getting closer and closer, and there I can see, I hope you can see it on the video, it's now out of focus. So I'm going to move it back somewhere around there. It's in pretty good focus. Let's check the distance. It's almost the same as where we started, I think, but it's a little bit closer, maybe about 32 centimeters. That's 32 centimeters from the object to the cornea. Now I'm going to add the 400 millimeter lens to slot B. And now we can see that the object is no longer in focus. Let me zoom in on the image, and you can see that it's out of focus. I'll move it in. There, it's in pretty good focus. I'll keep moving it in. There, it's starting to go out of focus again. So I'll move it back a little bit. Right about there is the closest I can get it and still have it be in pretty good focus. So let's check the distance from the cornea to the object. It's now about 22 centimeters. We're just making rough measurements here. All right, so now I'll remove that extra lens, the 400 millimeter. So now we're back to just the 62, and I'll move this back until it's in pretty good focus, so somewhere around there. So I'm going to add the pupil, which you can see is like this. First I'll zoom in on the image so you can see what happens when I add it. So when I put the pupil in place, you can see the image got quite a bit dimmer. Now let's see what happens in terms of how far in I can move and still have it be pretty well in focus. So I'm moving in, moving in, moving in. Still moderately in focus there. Let's get it sort of really out of focus. So there, that's pretty out of focus. I can barely even tell that the word top is there at all. Certainly can't read it, but I can tell that it is there, just barely. And so with the pupil in place, I can see that word is there at a distance from the cornea to the object of about 12.5. Now if I remove the pupil, let's see, now I can't see it at all. To get back to that equivalent level of clarity, I maybe have to get to about here, which is a distance of about 19.5 centimeters. So basically what we're seeing is that when you put the pupil in place, the image gets dimmer, but the focus becomes sharper. So there's pretty out of focus without the pupil because I'm too close in. I'm closer than the near point, but now when I put the pupil in place, you can see, although it gets a lot dimmer, the focus improves significantly. Let's just do one more demonstration. I'm going to pull it back a little bit without the pupil, so it's still clearly out of focus. And now when I put the pupil in, it's actually in pretty good focus now when I have the pupil in place, but obviously it's dimmer. Okay, so I have put the 120 millimeter lens in the septum position, and we're again looking at the window with the gooseneck lamp, and you can see that right now the image is pretty well in focus. So now I'm going to zoom out a little so you can see what I'm doing. I'm going to, as directed, move the retina from the normal position to the one that's labeled near, which is actually further away from the cornea than the normal position. So I'm going to move the retina to this near position, moving it back slightly, and now you can see the image. I'm going to zoom in on it so you can see it better, and you're called on to describe that. Now we're asked to put an eyeglass to make the image be in focus. So let me show you what they're talking about. Remember that there are these slots in front where we can put various different lenses. So for example, if I put a 307 millimeter plus 307 millimeter lens there, again, let me zoom back in on the image. You can see, boy, that just made it worse, right? Take that out, and let's try something else. Here's a 62 millimeter. Come on, get in there. That's awful. There's sort of almost no image at all. Just almost nothing. So that's no good. Let's try the 400 millimeter lens. It also makes it worse. So there's with that lens, there's without it. So that's no good. Let's try the minus 1000 millimeter lens. It's labeled minus 1000 millimeters. And holy smokes, image looks pretty good with that one.